So at the end of our last lecture, we derived the Henderson-Hasselbach equation. This time, let's look at some of the consequences of that. First, a buffer ignores volume. Sort of. Okay, take a look at the Henderson-Hasselbach equation again. Pay attention to the term over on the right, the log of the conjugate over the weak thing. Those are both in the same solution. So the concentration, moles over liters, is in the same volume for each of them. Moles over volume divided by different moles over same volume. The volume disappears. All that comes out of that is the moles of the conjugate and the weak thing. So, the pH of a buffer is going to stay constant as you dilute it, which is very handy. It's one of the reasons why your body's various pH levels stay where they are, no matter what you're drinking, whether you get a little dehydrated or a little bit over hydrated. Compare that to a non-buffer, HCl, hydrochloric acid, strong acid. If it has a concentration of 10 molar, then it has a pH of -1. You dilute that to a pH of 1 molar, or a concentration of 1 molar, it has a pH of 0. Dilute that again, its pH is just going to keep on going up, but that's not true of a buffer. It's important to note that this does not change the ability of a buffer to buffer. Okay? You can't dilute a buffer into infinite usefulness. The ability of the buffer to buffer depends on the actual atoms that are present. Okay? So you'll get the same pH, but it won't necessarily be as good a buffer, just because you're spreading your moles thin, as it were. The next thing to notice is that you need a 10 times change in concentration for a pH change of 1. Okay? So if you start out with equal quantities of your conjugate and your weak thing, equal concentrations, then you're looking at the log of 1, because thing divided by itself is 1, and log of 1 is 0. Okay? So your pH is just going to be equal to pKa, or your pOH would be equal to pKb. So what that would mean there is that in order to get a pH change of 1, in either direction, you're going to need a 10 times change in the concentration of either your conjugate or your weak thing. Okay? So if you're looking at a weak acid with a pKa of 5, you start off at equal concentrations, you'll have a pH of 5. And in order to get it up to a pH of 6, you would need 10 times as much conjugate presence as you have your weak acid. To get it down to a pH of 4, you need 10 times as much of your acid present as you have of your conjugate. So you really have to beat the hell out of a buffer to get the pH to change significantly. And when you do your own titration, you'll see that. Your pH for a buffer can remain largely unchanged for a long period of time, until it runs out of buffer capacity, and all of a sudden, boo, your pH just skyrockets. Or plummets, depending on which direction you're going. The other thing, this is less a direct consequence of the Henderson-Hasselbach equation and just the facts of powers of 10. Buffers work best in the region of pH equals pKa. So you want your pKa to really match the pH you want your system to stay at. And then it'll act as a really great buffer, plus or minus 1 of that pKa. So acetic acid vinegar would make a really good buffer around a pH of 4.7, because its pKa is 4.7. And then so it's still a good buffer up to a pH of 5.7 or down to a pH of 3.7. Beyond that, though, it's really lost too much of its buffer capacity. It's either lost too much of its weak acid or it's lost too much of its conjugate. It can't really act as a buffer anymore beyond that. So those are the three things that you should keep in mind about the Henderson-Hasselbach equation and the way buffers work. And now that we've talked about buffers, let's talk about titration. Titration is an incredibly useful, incredibly powerful laboratory technique. You can use it for all sorts of stuff. You have two solutions, one that you know a lot about, one that you're trying to find out something about. And you can use the known solution to find things out about the unknown solution. You can find the pKa of a substance. You can find the pH of a solution. You can find the concentration of a solution. You can identify a substance based on these characteristics. And titration extends well beyond acids and bases. You can use it for pretty much any solution-based chemistry, so long as you have some way of identifying when a reaction has been completed. Maybe there's a dramatic color change, maybe there's a change in some other property. It doesn't have to be pH. It could be conductivity. There's a whole mess of things you can use titration for. Color change is usually the one we go with, just because we have eyes and we like to use them. Most of us do, anyway. So let's look at some of the common features of titrations. So these are some examples of titration curves. On the left, you have a strong acid being titrated by a strong base. And on the right, you have a strong base being titrated with a strong acid. You can tell that because on the left, the pH starts low and ends up high. And on the right, it starts high and ends up low. And what you measure with titrations, that varies. But the way you usually track them is by looking at the pH. Don't get hung up on those two dotted lines and the pH of 7. That's only because it's a strong acid and a strong base in both cases. Okay? For most of the time, you won't be dealing with two strong things. You'll be dealing with a strong thing and a weak thing. Therefore, you're looking at a neutralization where the pH is going to be higher or lower than 7. So let's go ahead and look at a sort of example. Okay, here is an example of, a sketch, I should say, of a weak acid being titrated against a strong base. Okay? So the pH starts out low. It's still an acid, even though it's a weak acid. And then it swoops up and gets high because, we're adding base to it. Okay? So the first region of the graph we're going to look at is this steep climb here in the middle. Okay? That is known as the equivalence point because you've added an equivalent amount of base, just enough to neutralize it. Okay? The concentrations of your two solutions aren't necessarily the same, but the number of moles will be the same at equivalence. And you get this sudden dramatic change because you have switched from the buffer region of the weak acid into the buffer region of the conjugate base. So it's gone from wanting to maintain this acidic pH to wanting to maintain this basic pH. Okay, so it's a very dramatic jump. I mean, technically speaking, it's within the space of a few molecules. It's very, very steep. I won't go into exactly how you find equivalence right here, but that is something I can go into. It's very interesting, fairly straightforward technique. Now, what you do is you just go straight down from equivalence, and that gives you the equivalence volume. Remember, molarity times volume gets you moles, so you're going to need the volume so that you can find out how many moles of base you've added, and then that will help you find the concentration of your acid, sort of thing. Now, I also want to emphasize that the pH here will not be 7. It's going to be greater than 7, okay? Because you've jumped over into that basic range. Okay, a weak acid being titrated with a strong base is going to have a basic pH at equivalence. It's going to be greater than 7. So I just want to emphasize that at the equivalence point, the moles of base you have added to your solution are equal to the moles of acid you originally had. And that's kind of helpful because you've been doing not just a mixture this whole time. You've been diluting this whole time. So concentrations have been changing, but moles, those are forever. So let's move on from that to the 1/2 equivalence point. Okay, that's really straightforward, really easy to find. You just take the volume of equivalence, divide by 2, and that gives you the volume of 1/2 equivalence. Now, why do you want to find the 1/2 equivalence? Well, at 1/2 equivalence, you've added exactly half as much base as necessary to get you to equivalence. So you've added half the number of moles of base. And that gets you a neutralization of half of the acid. If you've neutralized half of the acid, well, that means you have half of the acid you started with and half of your conjugate. And if half of your solution is your weak acid, half of your solution is the conjugate base, well, let's just take a look at the Henderson-Hasselbach equation. pH equals pKa plus log of the conjugate over the weak acid. Well, if it's half and half, then that means they're exactly equal. And conjugate over the weak acid would be equal to 1, and log of 1 is 0, so pH equals pKa. So, you just look at your graph, and at 1/2 equivalence, pH is equal to pKa. And that is pretty darn good for, having only to do one mathematical calculation. That's dividing the volume by 2 to find the 1/2 equivalence point volume. And then you just go up on your line, and then you go over to the pH at that point. That's literally all you have to do. Like I said, titration is a very powerful tool. Just by taking this reaction and recording the pH all the way through, doing the analysis necessary to get equivalence, then all you have to do is divide by 2, and that gets you concentration and Ka with almost no mathematical work, which is almost unheard of in chemistry. Literally just the one math problem. Take the volume at equivalence, divide by 2, that gets you the volume of the 1/2 equivalence point. Right smack dab in the middle of the buffer region where pH is equal to pKa. That's pretty neat, I think. Not cool, but neat. So just to emphasize, one final little drawing picture thing. At equivalence point, the moles of base you've added are equal to the moles of acid you originally had. So just by finding the equivalence point, you find the number of moles of acid in your solution. You can find the concentration. And then that also gets you the 1/2 equivalence point where pH is equal to pKa. So those are the two really big things. Okay. At the equivalence point, you have your that sudden vertical spike. You found moles of base, moles of acid. And then you divide that by 2, you're right in the middle of the buffer region where pH equals pKa. And that does it for Chapter 14. There's obviously some math problems I can show you, and I will show you at some point, for titrations. But for now, I'm going to fall on my face and die for a little while.